Our last section for chapter 5 is about the quantum mechanical model. We'll be talking a lot about light and the electromagnetic spectrum. So some things that you all will be learning is how to describe the relationship between a wavelength and a frequency of light. Again, we'll be talking a lot about the atomic emission spectrum. We'll talk about frequencies and how to calculate them. And at the end, we will talk about the difference between quantum mechanics and classical mechanics. Someone wanting to discover more things about light led to the development of the quantum mechanical model. All light is a form of electromagnetic radiation, even light that we can't see. This includes any type of waves or rays such as radio waves, microwaves, gamma rays, X-rays, infrared waves, things of that nature. The equation that we use for this is the speed of light is equal to 2.998, or if you want to round 3, times 10 to the 8th meters per second. And it's abbreviated as c. So the speed of light is just given a variable of c. And all radiation travels at this rate when it's measured inside a vacuum. Okay, this is a diagram of the electromagnetic spectrum. It includes any waves and light that we can see and light that we cannot see. The lower energy would be more so on the left side. The energy goes higher as you move to the right. Frequency also increases as we go to the right, and wavelength decreases as we go to the left. Notice that the amount of visible light, or light that we can actually see, which are all of our colors, is just a very small portion of the spectrum. So most of the things in the spectrum are things that we can't see, such as the radio waves. We can't see radar. We can't see infrared rays or gamma rays, things like that. Waves have different parts. This might be some review from some of your integrated science classes. So where the wave actually starts is called the origin, obviously, because where something starts is called the origin. That makes sense. The crest is the very topmost portion of the wave. The trough is the bottommost portion. The amplitude is basically the distance between the crest and the trough. And then the wavelength is the distance between two waves. So any kind of radiation, it moves through space as a wave that's moving at the speed of light. The equation that we use for this is C equals lambda times nu. These are both Greek letters. So C is equal to the speed of light. We just talked about that in another slide. It's a constant, so that means the speed of light is always going to be this 2.998 times 10 to the 8th. It will not change regardless of the equation. Lambda, if you're wondering how to draw it, it's kind of like a upside down Y. That represents the wavelength, and it's measured in meters. And nu is just a V. That's pretty simple. It represents frequency, and the units for that are hertz. So wavelength and frequency have an inverse relationship, so that means when one goes up, the other goes down, and vice versa. Different frequencies of light are different colors of light. The color basically comes from the different frequencies. And there's a wide variety of frequencies, as you saw on the spectrum diagram that I showed you. And that whole entire range of colors and waves is called a spectrum. This is an example of how we would use our equation to calculate the wavelength of light. So in this equation, you were given the frequency. It's not giving you the speed of light because the speed of light is a constant, so you will be expected to know automatically that that is what it's supposed to be. It will not necessarily be given to you. So if we wanted to manipulate this equation so we could just find the wavelength, we would make it C over V equals the wavelength. So this is our C, this is our V. So if we were to divide C and V, we would put that in the calculator, and the number we would come up with would be about 5.88 times 10 to the -7 meters. This is very simple math. It's not any more complicated than any of the other things that you've been doing. This is another picture of the electromagnetic spectrum. So the energy is lower on one side, on the left side, and also with low energy comes low frequency and a longer wavelength. So that would be your radio waves, microwaves, things like that. Visible light, again, is in the middle. This is the light that we can see. It's all of our colors. High energy is on the other end with gamma rays. And with high energy comes high frequency and a short wavelength. Okay, this is a better picture also of what I was just talking about in the last slide. So again, when you have a long wavelength, that means the frequency is going to be low and the energy is going to be low. So if you have a longer wavelength, like in this first picture, the frequency of the wave is not going to happen as often because the wavelengths are longer. And because of that, the energy is going to be a little less because it takes less energy to make a lower frequency wave. Notice how with this one, this is like 8 cycles per second. Notice the wavelength is a little bit shorter. So the frequency of the waves, or how many waves it makes, is a little higher. At the bottom, the wavelength is even shorter, and notice how many waves there are. So that means the frequency got higher, and that means it also has a higher energy. Okay, when we see the color white, it's basically all the colors in the spectrum put together, and that is what comes out when we see it. And when it passes through a prism, that's what separates the colors from each other. If the light isn't already white, we can heat it up with some electricity and get it to give off other various colors. When we pass that light through a prism, it does something a little bit different than the other one does. Each element gives off its own characteristic colors. So like hydrogen would give off a different color than bromine, and that would give off a different color than oxygen, etc., and etc. This is a way that we can identify various atoms. And this is also how we know what different stars are made of. So when all these different elements make their own special colors, this is called the atomic emission spectrum. This is unique to each element, just like you are unique from everyone around you because you have different fingerprints. These are like fingerprints for the elements. And again, it's very, very useful in identifying the elements. Okay. So light is also considered a particle, and the energy is quantized, just like the electron energy is quantized. We talked about that previously as well. Light is also a form of energy. We also talked about maybe a chapter or two ago that one way to tell that a chemical reaction is taking place is that some form of light is given off or heat. This, again, is part of what reinforces that it's a form of energy. So since energy is quantized and light is a form of energy, that means that by definition light must be quantized. So the smallest pieces of light are called photons. Albert Einstein came up with the photoelectric effect, and just know that energy and frequency are directly related, which means that when the energy goes up, frequency goes up. When energy goes down, frequency goes down. They move in the same direction. The energy of any kind of electromagnetic radiation is directly proportional to the frequency. So again, that means that they move in the same direction. So when energy goes up, frequency goes up, and vice versa. The equation that we use for this is energy equals H times V. Energy is denoted by a capital letter E. It has the unit of joules. Joule, again, is a metric unit of energy. We talked about this maybe the first chapter. H is another constant. It's called Planck's constant. Remember, if it's a constant, that means it will not change. Just like in your math classes, pi is always 3.14. Well, any constant that we have in chemistry is just like that. The number is never going to change. So Planck's constant is this 6.626 times 10 to the negative 34th. Again, it does not change. And V is still frequency, and the units are still hertz. Okay, I'm sure you guys will be very happy about this. This chapter does not have a lot of math. The only two equations that I'm going to expect you to know for this chapter are the two that we've gone over. So that's the speed of light equals wavelength times frequency, and energy equals Planck's constant times frequency. I will more than likely not give you these on a test, so please make sure that you know these. It's very important. Okay, now we're going to do some examples of some of the calculations that you'll have to do with some of these equations. So this question is giving you the frequency and you're asked the wavelength. So we're going to use our equation C equals the frequency times the wavelength. Remember, because C is a constant, it will not necessarily be given to you all the time. In an equation, you're going to be expected to just automatically know that it belongs there. So if we wanted to manipulate this equation just to get the frequency by itself, we could rewrite it as C over V equals the frequency. So if we want to go ahead and start this, C again is a constant, so that's the 2.998 times 10 to the 8th. And then it'll be divided by the frequency that was given to us, which is 8.3. Point didn't come out so well. 8.3 times 10 to the 15th. So if we were to divide both of those and put them in the calculator, it would come out to 3.61 times 10 to the negative 8th meters. Okay, this next problem is asking for the frequency, and we were given the wavelength, so we'll use that same equation from the previous example. C equals the wavelength times frequency. So now this time, because it's asking us for frequency, if we wanted to manipulate that to get frequency by itself, we would have C divided by the wavelength equals frequency. So again, C is our constant. So we should automatically fill that number in because, again, it's not going to change ever. So we would divide C and the wavelength we were given, which is 4.2 times 10 to the negative 5th. Once we get that into the calculator and hit our equal button, our answer will be about 7.14 times 10 to the 12th. And because it's frequency, our units are hertz. Okay, this next question is asking us the energy of a photon of each of the previous atoms that we were just looking at. So we would have to use our E equals HV equation because that's the only one we have for energy. So again, don't forget that H is a constant, so it's always going to be the same number. So again, it will not necessarily be given to you. You will just be expected to know what it is and when you're supposed to use it. Okay, so for the first example we did, the frequency was 8.3 times 10 to the 15th. So all we have to do is just plug that into our equation. So E equals H, which is Planck's constant, which is 6.626 times 10 to the negative 34th times our frequency, which is, again, 8.3 times 10 to the 15th. We get all that into the calculator. It comes out to 5.5 times 10 to the negative 18th, and the units for that would be joules. So now for the next one, we're going to use the same equation because it's still asking us for the energy. So now for our second one, we found the frequency to be 7.14 times 10 to the 12th hertz. So again, we're going to have our energy equals our Planck's constant, 6.626 times 10 to the negative 34th. And then we will multiply that by the frequency that we found for the second question. Once we get all that into the calculator, it will come out to about 4.7 points are not coming out well for me. Times 10 to the negative 21st. And again, because it's energy, it would be measured in joules. And that would be our final answer for that one. Okay, so just a quick explanation of the atomic spectrum. Whenever we write our electron configurations, which you guys are very familiar with because we did it all this past week, we're writing the lowest energy. Remember when I started explaining the electron configurations to you, I told you that according to that off-bow diagram, the one with the arrows, that we fill up the lowest energy levels first. So again, this goes with the whole we're writing the lowest energy. So the energy level and where the electron starts from is called the ground state. And again, that's the lowest energy level because it's on the ground, it's the bottom, so it would be the lowest. Okay, so as far as changing energy, we're going to take a look at a hydrogen atom. This is our picture of a hydrogen atom. So the hydrogen atom only has one electron in that first energy level. Anytime we heat up something or we add electricity or light to it, that gives the electrons a little more energy so they can move up to different energy levels. Once the electron gets this certain amount of energy or a quantum of energy, it's now said to be an excited electron. Once the electrons get excited, they basically flip out and they can go and jump levels and go play with the other electrons. As the electron falls back down to ground state or it comes down off of its little sugar high that it's been on that causes it to flip out and go everywhere in all the other energy levels, it gives that energy back as some kind of light. So the further these electrons fall or the more they come down from their little random sugar high, the more energy is released and the higher the frequency. So the more energy that gets released, the wavelengths are going to be a little shorter, which again will increase the frequency. This is a very simplified explanation. If you were to take one of these types of classes in college, they would go into much more detail than you probably would even want to know. So the orbitals for each electron also have different energies inside their energy levels. And just remember that all electrons can move around. So just to define light in general, light is a particle. It comes in chunks, which is again why it can be quantized because energy can be quantized in chunks. Light is also a wave. We can measure its wavelength and it also behaves as a wave. If we were to combine Albert Einstein's equation that E equals mc squared, our equation for the speed of light that we learned, and then energy equals 1/2 mv squared, and our other equation that we just learned where energy equals Planck's constant times frequency. If we combine all of those together, we can get one very simple equation, which is wavelength equals Planck's constant divided by mv. This is from a scientist named Louis de Broglie, so it's called the de Broglie equation. And basically what it does is it calculates the wavelength of a particle. That's the sole purpose. So quantum mechanics describes how very small particles behave. And this is also an explanation for the subatomic particles like the protons, neutrons, and electrons, and atoms as waves. Classical mechanics describes the motion of things that are a lot larger than atoms. So quantum mechanics deals with things that are very small. Classical mechanics deals with things that are large. So it's pretty much impossible to know the exact location and velocity of a particle just because they're moving entirely too fast and it's very hard to just pinpoint them and tie them down to one spot. But the better we know one, the less we know about the other. It gives us a certain level of uncertainty, which is why this is called the Heisenberg uncertainty principle. This principle basically measures the changes in the properties. It's true for quantum mechanics, but it does not work for classical mechanics. Okay. That will conclude chapter 5. The next chapter we'll talk about will be the periodic table. If there's anything you are confused about, please feel free to watch this video again.